We have always been fascinated by it. And that is why, over the past 40 years, we have sent 8 spacecraft to investigate this massive world. But its swirling cloud tops still conceal many mysteries. And that is why we have now sent a 9th mission, Juno.
There it is, Juno right on time, into orbit, exactly as planned. Last Monday, NASA's Juno probe arrived in orbit around Jupiter. The Sky at Night has been embedded here at Mission Control, and so tonight we bring you all the action as Juno completed the most dangerous and complex phase of its mission.
We'll also be looking forward to what Juno does next, and how it's set to transform our understanding of the solar system. Welcome to the Sky at Night.
This is the Jet Propulsion Laboratory in Pasadena, California, one of the iconic sites of the space age, home base for our exploration of the solar system. It was from right here that the world watched as the Voyagers and the Pioneer spacecraft made their first reconnaissance of the giant planets. And now, with Juno, we're going back to Jupiter. In Roman mythology, Juno was Jupiter's wife, the only person who could see through the clouds that concealed her husband. Juno the spacecraft's mission is exactly the same. Its aim is to peer through the clouds to reveal what's going on inside the planet.
The mission has 3 main objectives: to understand what drives Jupiter's violent atmosphere, to discover how the planet was formed, shedding light on the formation of the entire solar system, and to find out why it has such intense and spectacular aurorae.
But first, it had to enter an orbit that would take it within 5,000 kilometers of the giant planet. The crucial maneuver was called Jupiter Orbit Insertion. And with a certain sense of theatre, it was set for the evening of the 4th of July. That morning, Juno scientists and the world's media gathered at JPL to watch events unfold. This was to be one of the most crucial days in the whole mission. And the greatest fear was that the spacecraft might not make it through the hostile environment close to the planet. Can you say what we know about the ring particles that you were worried about?
We believe the probability is incredibly low that we're going to hit one, but it's not 0. It's the same thing if I go through the asteroid belt, you know. And so as we fly by very, very close, we look at the signal from the radio and can tell how it's being changed.
I've just come out of the briefing with a quite nervous-looking Juno team. They're excited, but they're clearly worried about whether the spacecraft will survive the next 24 hours. But I have to show you this. This is the first movie we've seen from Juno Cam. It's about 2 days' worth of an approach to Jupiter. What I love about it is you can see the main moons, the 4 Galilean moons, dancing around the planet. You can see Jupiter growing as it approaches over the course of this movie. That means it's crunch time. Juno is entering the most dangerous phase of its mission, and what the team in the briefing there are worried about is dust from the rings. A single collision could end the mission. And the team are also worried about the radiation environment. That could stop Juno working and put a very premature end to the mission. To get into orbit, Juno had to fire its main engine, slowing the probe down just enough to be captured by Jupiter's gravity. Its trajectory had been carefully planned to avoid the worst of the planet's radiation belts. It would approach over the North Pole before falling into an orbit that would repeatedly squeeze Juno between the radiation belts and the planet itself. No spacecraft had ever attempted such a daredevil maneuver. I spoke to Juno scientist Fran Bagnall about the dangers. So we're not far off now from the critical moment, the engine burn that will deliver Juno, with any luck, to its desired orbit. How are the team feeling? How nervous are you?
We're all worried and nervous, and I'm sure everything will go fine, and I trust the engineers. But yes, I've got all my fingers and toes crossed.
So we've been to Jupiter before. We had the flybys, but also the Galileo mission that went into orbit and explored the Jovian system. What's different about this time? What is it that's dangerous?
Usually when we go to Jupiter, we're either getting a gravity assist and we stay away from the inner region, or we're going in orbit and we stay in the equator. Now, for Juno science, we really want to get up close. Right around the belly of Jupiter, there is a donut of very energetic charged particles, 10 million electron-volt electrons that are whizzing around, which is a lot, right? And so you're really worried that the electronics will be zapped by these energetic particles and damage the sensitive electronics you've got inside in detectors. It's like taking your computer and giving it a gazillion X-rays, you know, you wouldn't want to do that. So what we're going to do is very clever. We're going to fly over the top of the pole. We're going to fly through the slot between the radiation belts and the clouds, through that region and then out again below. And that, we hope, will protect us from those energetic radiation belts.
And how small a slot is that? How much of a precision maneuver does this have to be?
We don't really know, because we don't really know how far the atmosphere extends out. And we don't really know what the radiation belts are. We can map them from the ground using radio observations, but they're not that accurate. So it's not so much an issue of precision as uncertainty, and we don't really know what it's like. This is terra incognita. The other thing that makes this a little safer is that because of Jupiter's strong gravity, we're moving really quickly. So we go in through there and get out really quickly. And so the spacecraft will be moving at about 165,000 miles an hour. And so this allows us to go from pole to pole in 2 hours. And since Jupiter is 10 times the size of the Earth, that's equivalent to going around the Earth 5 times in 2 hours.
Wow. It's a dangerous mission, nearly 2 decades in the making, and it could end in disaster before it starts. So what is it that we want to know about Jupiter that justifies these risks?
Jupiter dominates our solar system. It's 140,000 kilometers across, and 2.5 times more massive than the rest of the planets put together. On this scale, if Jupiter were the size it appears on the screen, about 2.5 meters across, then the Earth would appear the size of this basketball, and it would fit into Jupiter about 1,000 times over. We think that Jupiter was the first planet to be formed. It sort of hoovered up most of the stuff left behind after the Sun's formation. And like the Sun, it's mainly made up of hydrogen and helium, about 95%. The other 5% is made up of heavier elements. And it's all spinning incredibly fast. This vast planet rotates on its axis once every 10 hours. As it spins, the clouds of its atmosphere are driven into thick bands by the powerful winds that orbit the planet. Those swirling forces create giant storms, like the famous red spot. Even though we've been studying the planet for over 400 years, there's still much that is quite mysterious about Jupiter. One of the first things Juno is aiming to discover is what powers those giant storm systems. To find out how it's going to do that, I went to talk to Jupiter expert and Juno collaborator Lee Fletcher. So Lee, what are we seeing here?
This is actually a beautiful movie that was taken by the Cassini spacecraft when it flew by Jupiter back in the year 2000, 16 years ago. So you can see in this image just how dynamic the Jovian atmosphere is. Things are changing all of the time as we have these jets of wind whizzing east and west and separating the beautiful banded structure. And we think that these bright white clouds at the equator are regions where air is welling up from the deeper interior and it's dredging with it particles or molecules of ammonia gas. And those ammonia gas molecules condense and it forms ice crystals. And those ice crystals create these white colours within the equatorial zone.
OK, that's the white bands, but how about these darker bands?
Now, that's an even harder question to answer, unfortunately. But, of course, what comes up must then ultimately go down. And what we believe is happening is the air that's rising over the equator is then sinking over the northern equatorial belt and the southern equatorial belt. Those ice crystals evaporate away, and they reveal the natural colours of Jupiter deeper down within the planet. Unfortunately, we still don't know what is actually causing the brown colour. What you can see here as well is that the belts look much more active and much more dynamic than the white regions. And we think that all of that activity is being driven by the same molecule that drives atmospheric weather here on planet Earth, and that's water vapour. You're familiar with if you have a humid atmosphere, it's more prone to thunderstorms, tropical storms,
hurricanes and things.
Well, the same phenomena could be occurring within Jupiter. But if water is part of the story for what's driving this incredibly dynamic atmosphere, then we'd have to understand where the water is located within Jupiter and how much, crucially, how much is there within the planet.
So how can we do that? Can we go any deeper?
So Juno's got a very clever instrument called a microwave radiometer on board. And what we can see in microwave light is modulated by the amount of ammonia that's there and the amount of water that is there. So by building up this map, and it will take a while to build it up, many months of the Juno mission going over various longitudes to paint a complete picture of the planet, we'll then be able to map where the water is located and where the ammonia is located.
So that might give you an understanding of what's driving those weather systems.
Absolutely. Juno is going to be a step change in our understanding of how much water is present within the Jovian atmosphere.
But Juno's mission is about more than just studying Jupiter's upper atmosphere. By probing the deep interior, it hopes to reveal how both the planet and the solar system formed. One of the great mysteries of Jupiter is understanding how it formed in the first place. One possibility is that it began life as a star does, as a collapsing cloud of gas before becoming the planet that we see today. Another option is that, big though it is, Jupiter began life in the same way that the Earth did, starting as nothing more than a pile of rubble, planetesimals that could stick together to eventually form a core that was maybe 10 times the mass of the Earth, big enough to grab and to hold on to a thick hydrogen atmosphere. Juno will tell us which of these two possibilities is the correct one. As it orbits the planet, Juno's path is not completely uniform. It's affected by tiny variations in Jupiter's gravitational field. By tracking these tiny wobbles over the months that it's in orbit, Juno will build up an incredibly detailed map of the planet's gravitational field. And that should tell us whether or not there's a rocky core at the heart of Jupiter. Either way, it's a discovery that will have profound implications for our understanding of how giant planets form, not just in our solar system, but also in other solar systems, around other stars. Juno has amazing scientific potential, but before it could start its observations, the spacecraft first had to complete its orbit insertion maneuver. Back in mission control, while the rest of America was out celebrating the 4th of July, we waited for news. So just a few minutes ago, out near Jupiter, Juno should have started firing its main engine. It's the critical maneuver required to take it into orbit around Jupiter. The only problem is, because it's so far away, it'll take 48 minutes for that signal to reach us here at Mission Control. And only when it arrives will people start to breathe a little easier. We're expecting a signal from the spacecraft to say all is well, and then 2 minutes later, confirmation that the burn has started. I think it was quite jovial, but it's all gone very quiet and very tense. People know if this doesn't come in on time, something is seriously wrong.
Everything's looking good.
Standing by.
We're right on the time we expected the signal.
Systems of snap.
Good enough?
Yeah, we see the expected sharp
Got it.
shift
I've got it.
upward.
It's changed its velocity, the burn has started, and Juno is starting to put itself in orbit. Well, that's wonderful news. The fact that the burn has started means the engine is working as expected. But the really difficult bit is keeping it working as Juno travels through this most dangerous region. They need a burn of 35 minutes to put themselves in the desired orbit, so people will be keeping things crossed for a long time yet.
In order to make all its measurements and to probe beneath Jupiter's clouds, Juno has been equipped as no spacecraft ever before. I used to build instrumentation for spacecraft, but I've never been involved with anything like Juno. For one thing, it's huge, about 20 meters across. That's about the width of this hangar. Most of that width is made up of these huge solar panels, each one 9 meters long. Now, the reason we need such large solar panels is because Juno is going to sit a long, long way away from the sun. Out around Jupiter, the sun's intensity is just 1/25 of what we receive here on Earth. It's the first time we're sending a solar-powered spacecraft so far into the solar system. The 18,700 solar cells will only produce around 450 watts. It's not much, not even enough to boil a kettle, but Juno's instruments have been designed to operate at low power. The spacecraft's brain and most of the instrument and electronics are housed in this titanium vault to protect it from radiation. But the instruments themselves are based on the outside of the spacecraft. The first instrument is JEDI, used to measure high-energy particles in Jupiter's magnetic field. These are the microwave detectors. They'll analyze water in Jupiter's atmosphere. And this is the only optical camera on board, JunoCam. And as it was leaving the Earth, it took this magnificent picture. It really is quite beautiful, but the images JunoCam will take of Jupiter will be far more spectacular. At its closest approach to the planet, it will be only 4,200 kilometers above the cloud tops. That might sound like a lot. So let's use our basketball again, only this time it's Jupiter. On this scale, Juno will fly less than a centimetre above the surface. And from that location, it will be able to take the highest resolution images of Jupiter that have ever been seen. This is the part of the mission we can all take part in, because NASA have asked for the public's help in choosing the features that JunoCam will photograph. And as Peter's been discovering, the first step is that they want people to submit their own photos of Jupiter.
Right, I'm nicely lined up on Jupiter now, and it's actually a pretty good view. The planet is getting lower in the sky, and it'll get even lower throughout July as it gets closer towards the sun. So what I'd say is sort of wait 20, maybe 30 minutes after sunset, and then look for the brightest star-like object, which is low down in the western part of the sky, and that should be Jupiter. Okay, the view is a little bit wobbly tonight, but you can still make out the main features. You've got the two main belts running across the planet's disk, and you can see the gaps in between them. And if you look very carefully, you can see the undulations and other features which are along those belts. So what you need to do once you've got your image is send it up to the Juno website. They are processed into a composite map of Jupiter that's constantly updated to give the most accurate view of the planet's atmosphere. And then everyone, even those who haven't got a telescope, can take part. When Juno goes into its secure orbit, it will be possible to vote for the most interesting features, and the most popular ones will then be the target for JunoCam. The first really detailed images will be taken as Juno sweeps past Jupiter's atmosphere on August the 27th, and the first raw data will be released soon after that. Now, this will give us the most detailed view we've ever had of Jupiter's clouds. So who knows what surprises and 3D structures we're going to see. It's really going to be an exciting few months.
But there's one more mystery that Juno will hope to solve. And that is the mystery of Jupiter's aurora that blaze in ultraviolet light and high-energy X-rays. They are like the Earth's northern lights on steroids. But our current understanding of the physics cannot explain why they are so extensive. Part of Juno's mission is to find out exactly how these aurora are generated. On Earth, the aurora are caused by the interaction of the magnetic field with the solar wind, the flow of particles that stream from the sun. Something similar must be happening on Jupiter. But there's a problem. At this distance from the sun, the solar wind is much too weak to generate such a bright display on its own. Chris tracked down planetary scientist John Nichols to find out how Juno is going to help decode Jupiter's remarkable aurora.
So these are amazing images, but what exactly are we seeing?
So we're seeing Hubble observations of Jupiter's ultraviolet auroras. These are the auroras here. Now, auroras are formed when charged particles trapped on a planet's magnetic field travel down the magnetic field and hit the atmosphere and make it glow.
Try to imagine what it would be like looking at these aurora if you could somehow stand and look up at Jupiter. How strong are they compared to Earth's aurora?
So typically the auroras are about 100 times brighter than they are on the Earth. In fact, during our campaign, we've seen the auroral brightness really increase dramatically to about 1,000 times what you'd see on the Earth. Now, if you could see these are obviously ultraviolet taken with the Hubble Space Telescope, but if you could float in a balloon in Jupiter's atmosphere and look up at these, you'd see a curtain of red. It would be bright red, and it's 1,000 kilometers high, and it would extend from one horizon to the other.
An auroral display of this magnitude requires a constant and plentiful supply of charged particles which can become entangled with Jupiter's magnetic field. Scientists think they've identified that source. It is Jupiter's moon, Io. Io is the closest large moon to Jupiter, and it's highly volcanic. Every hour, its volcanoes spew tons of material into the magnetic field that surrounds the giant planet. That material becomes electrically charged, interacting with Jupiter's magnetic field lines and creating the aurora where they intersect the planet's atmosphere. It's an extraordinary idea, but it's backed up by some remarkable evidence. As Io orbits, it leaves its footprint, drawn brightly in the aurora. I love the fact this is due to volcanoes on a moon and we see it on the planet. That's quite cool. What about the rest of this structure? There's an awful lot going on here.
Yeah, so this is the Io footprint here, and then we've got the main auroral oval, which is also driven by material from Io, but then we've got all this stuff in the middle, and we really have no idea what drives that. We think that it might be due to something to do with the solar wind. The solar wind drives the Earth's auroras, but we have no theories in our magnetospheric physics that tells us that we should see something like this. So we really have no idea what's causing that.
And to understand that, you need to know what's coming in, you need to understand the magnetic field, and you need to know what's going on in the planet itself. It's sort of a really complex problem.
That's right, and that's why Juno is the perfect spacecraft to tell us exactly what is going on here. Juno is going to fly over this region for the first time, and it's going to tell us what the magnetic field and the plasma is doing in this region, and it's going to reveal what's causing this.
And if there was one thing that you could find out about Jupiter, you only get one answer to a question from the Juno mission, what would it be?
I want to know what is causing this. I really want to find the answer, what is giving us all of these sparkles and flashes and pops going off here.
As the end of the Jupiter orbit insertion approached, things at Mission Control were increasingly tense. We're into the last few minutes of the burn, and so far everything's gone perfectly. Now we're waiting to hear for news that it's shut off successfully. If that doesn't happen, Juno only has about 10 minutes to recover before it plummets into Jupiter itself.
All stations on Juno Court, it's time we see the tone for minimum burn timer. Almost there.
That's the warning that the end of burn is imminent. Should be seconds away from having a spacecraft in orbit around Jupiter. There it is! There we go, Juno right on time, into orbit, exactly as planned. We have a spacecraft in orbit around Jupiter. I think people are rather pleased. It's a very, very relieved team. I think they began to believe it was going to happen, but for it to happen exactly on cue is an astounding feat of engineering.
Burn time was 21:02 seconds, only differing 1 second off of the pre-burn predictions.
They were 1 second off their planned burn. To fly a spacecraft that far and have it work that well is an incredible feat.
But now it's in orbit, it's time for the real mission to start. Juno's first 2 orbits are very long, allowing it time to turn its instruments back on and calibrate them in the hostile environment around Jupiter. But then the engines will burn again, putting it into a shorter orbit, just 14 days long, an eccentric orbit that will take it from over 2 million kilometers from the planet to less than 5,000. Around the middle of August, the serious science will begin.
Welcome to Jupiter. Congratulations.
Yay!
So it went well then?
It went great. Just, I mean, what were they, like 1 second off or something ridiculous?
Perfect.
It's perfect. So now we got the work is going to start. We get the data, we got to do the work. But it's great. It's, oh.
Did you believe?
Fantastic.
Were you just sitting there relaxed, or was there
Oh, I was like, you know. Anyway, it went well.
But the next time you fly past Jupiter in less than 2 months' time, the instruments are on.
So the 27th of August is the key day when we do this first, all science on, engines off, so no distractions, and we get the data, and that's going to be really key because we go through the aurora, we get up close, we look at the microwave, we try to find out the first set of water. We're not going to be mapping, but at least getting the first taste of Jupiter. And we'll see what it's like.
Yeah, well, we're looking forward to it.
It's gonna be
Congratulations.
great. Sure.
Enjoy.
Pleasure.
Come and tell us
Okay,
about it.
I will.
Take care.
Good.
Well done.
Okay.
Thank you. What a wonderful night. I can hear 4th of July fireworks going off all around me, but up there in the sky is Jupiter, and we now know that there's a space probe orbiting that tiny point of light. Juno performed perfectly, placing itself in prime position to solve the mysteries of this giant planet and tell us lots more about the history of the solar system.
We'll be reporting on Juno's discoveries in the coming months. But that's it for now, and there's no programme next month. We'll be back in September. In the meantime, go to our website to see Pete's Star Guide and to find out more about Jupiter, including what we can learn about the planet by examining it in the infrared, and the strange physics at work in its core. But, as always, get outside and get looking up.
The best of Tea in the Park here on BBC4, beginning with Jake Bugg next.